The universe might contain a hidden self-destruct button. This is the chilling possibility of vacuum decay, a quantum bubble that could unmake reality itself. By the end of this exploration, you will understand the science behind this ultimate cosmic catastrophe and what it truly means for our existence. We will uncover whether our reality is built on a foundation of sand, and if this unthinkable event could already be racing toward us, invisible and unstoppable. How would you react if you learned the laws of physics are only temporary? We often think of empty space as just that, empty, a perfect, silent void where nothing happens. But the universe has a secret. In the realm of quantum physics, there is no such thing as true nothingness. What we call a vacuum is actually a dynamic, humming arena, the lowest energy state possible for the fields that make up our reality. Think of it like the surface of a calm pond on a windless day. It looks perfectly still and flat, the most peaceful state you can imagine. But just beneath that glassy surface, the water is teeming with microscopic life and constant, subtle motion. The quantum vacuum is that pond. It is not empty. It is filled with a seething froth of virtual particles flickering in and out of existence, governed by fundamental fields that give particles their mass and charge. This state, this calm pond, is what physicists call the true vacuum, the most stable, lowest energy configuration we have ever observed. But here is the unsettling question. What if our pond is not a pond at all? What if it is actually a vast, shallow puddle resting on top of a mountain? It looks stable, it feels permanent. But it is not the lowest point possible. In this analogy, the mountain represents a staggering drop to a far deeper, more stable state of reality, a state with even less energy. Our universe in this scenario would not be in a true vacuum. It would be in a false vacuum, a metastable state. It is peaceful and predictable, but it is perched. It exists in a temporary valley of stability, separated from a deeper, more fundamental valley by a sheer cliff of energy. For now, the ground holds. The laws of physics as we know them, the forces that bind atoms and allow stars to shine, all depend on us remaining in this particular valley. But the potential for a catastrophic transition, a slide into that deeper, truer state of nothingness, would always be there, written into the fabric of space itself. This is not about something invading our universe from the outside. The danger is baked into the foundation of everything we know. Our entire reality depends on a single, invisible field. This is the Higgs field, an energy that permeates every corner of the cosmos. To understand its role, we need to go back to the universe's first moments. In the extreme heat just after the Big Bang, the fundamental forces of nature were unified, and the Higgs field was in a state of perfect symmetry, its value hovering at zero. Particles raced around at the speed of light, massless and free. Then, as the universe expanded and cooled, something monumental happened. A cosmic transition known as electroweak symmetry breaking took place. The Higgs field, like water freezing into ice, settled into a new, non-zero value everywhere at once. This sudden shift gave mass to particles like electrons and quarks, slowing them down and allowing them to clump together into atoms, stars, and eventually, us. That specific value the field chose is why a proton has the mass it does, and why chemistry works the way it does. It defined the very vacuum state we call home. But physicists have a haunting suspicion. The mathematical shape that describes the Higgs field's energy, called its potential, might not be the simple, stable bowl we hope it is. Imagine a ball resting in a small dip on the side of a much larger hill. The dip is stable for now. The ball isn't moving. That's our universe, sitting in what we perceive as its lowest energy state. But the hill slopes down to a vast, deep valley far below. That valley represents a truer, more stable vacuum, our dip, our entire reality, might just be a local minimum, a temporary resting place on a much grander landscape. This means the constants of nature, the very laws of physics that feel so absolute and eternal, could be nothing more than a cosmic accident, a fleeting configuration. The stability of everything you see, touch, and are made of hinges precariously on the configuration of this one quantum field. It is a breathtaking and humbling thought that the universe's deepest laws might be provisional. And if that is true, then the mechanism for their undoing is already written into the equations. The stability of our universe is a fragile illusion, maintained only by a quantum coin toss. Within the seething energy of the false vacuum, the rules of the subatomic world provide a terrifying escape clause, a process known as quantum tunneling. Normally, to roll a ball out of its stable dip and down into the deeper valley, you would need to give it enough energy to climb over the hill. But in the quantum realm, particles and fields do not play by those rules. There is a vanishingly small, but non-zero, probability that a region of space can simply appear on the other side of that energy barrier, as if it teleported through the mountain itself. This is not science fiction. It is a fundamental, well-understood quirk of reality, the same phenomenon that allows radioactive atoms to decay or enables the nuclear fusion that powers our sun. In our cosmic context, it means a microscopic bubble of that truer, lower energy vacuum could spontaneously nucleate anywhere in the universe at any moment. Picture a supercooled glass of pure water. It remains liquid well below its freezing point, looking perfectly clear and still. But the introduction of a single speck of dust, or even a random jostle of its own molecules, can trigger an instantaneous and catastrophic chain reaction. The entire volume crystallizes into ice in a flash, racing outward from that single point. The birth of a true vacuum bubble would be infinitely more violent. It would begin smaller than a subatomic particle, a perfect sphere where the Higgs field has tunneled into its new, fundamental state. The moment it forms, physics as we know it ceases to exist within its boundary. The constants that govern forces, the masses of particles, everything that gives structure to matter would be rewritten into an alien and likely barren set of laws. But the true horror lies not inside the bubble but at its edge. The wall of this sphere is a frontier of unimaginable energy density, a shockwave of redefined reality. And this wall would expand not like an explosion but like a change in the very nature of space, propagating outward at nearly the speed of light. The trigger is utterly random, a quantum fluctuation in the background hum of empty space. It could happen in the void between galaxies a billion light-years away, or it could, in theory, nucleate right here in the room around you. There is no way to predict it and no way to see it coming. This transforms the cosmos into a lottery of existential stakes, where every point in space holds a ticket, and the grand prize is the irreversible end of everything familiar. The moment that bubble appears, a new universe is born within the old. Its wall is not made of matter or energy as we understand them. It is a boundary of pure transition, a rewriting of the cosmic rulebook propagating outward at the speed of light. Nothing can outrun it, for it is not moving through space so much as it is redefining the very space it occupies. As this frontier sweeps through a region, the Higgs field within it drops to its new, fundamental value. The consequences are instantaneous and absolute. The properties we assign to particles are not inherent. They are gifts bestowed by the Higgs field. In the new vacuum, those gifts are revoked and replaced. An electron might suddenly weigh 1,000,000 times more or lose its charge entirely. Quarks, the building blocks of protons and neutrons, could cease to interact via the strong nuclear force. That force is the glue that holds atomic nuclei together. Without it, every single atomic nucleus in your body, in the Earth, in the Sun, would simply fly apart in a silent flash of elementary particles. But the devastation is even more thorough. Electromagnetism, the force behind light and chemistry, and the structure of atoms themselves would also be reconfigured. The delicate balance of attraction and repulsion that allows electrons to orbit nuclei and atoms to bond into molecules would vanish. The entire periodic table, every compound, every strand of DNA, every crystalline structure in a rock would cease to have any meaning. The universe behind the bubble's wall is not a place of destruction in the conventional sense. There is no explosion, no fire, no sound. It is a place of erasure where the laws that allow for complexity and structure are simply switched off. A star would not explode. It would, in a literal sense, unmade, its atoms dissolving into a cloud of unrecognizable fundamental entities governed by alien rules. A planet, a person, a thought, all are patterns written in a language of physics that no longer exists. The bubble translates them into a new, likely barren, tongue, and in that translation, everything they were is lost. This wave of transformation would be utterly silent, completely invisible until the moment it arrived, and there would be no warning, no aftermath, and no one left to record the change. The old universe is not replaced by chaos, but by a different, simpler order, one where the story of stars, planets, and life could never be written again. The new vacuum would erase the concept of matter as we know it. Our entire experience of the physical world relies on particles having specific, stable properties. But inside that expanding sphere, those properties are not just altered, they are replaced by an entirely different set of rules. The mass of an electron, which dictates the size of atoms and the nature of chemistry, is not a fixed number. It is a value set by the Higgs field. If that field finds a new, lower state, it resets the dials. Particles could become unimaginably heavy, collapsing instantly into bizarre forms, or they could become utterly massless, zipping away at light speed and never interacting again. More critically, the forces that allow particles to bind together might simply cease to function. The strong nuclear force, which overcomes the fierce repulsion between protons in an atomic nucleus, could vanish. Without that glue, every single atomic nucleus in the universe would disintegrate in an instant. A carbon atom in your DNA, an iron atom in the core of a star, a silicon atom in a distant moon rock, all would silently dissolve into a diffuse mist of unbound quarks and gluons, a form of matter so exotic and unstructured it bears no resemblance to anything in our current reality. This is not a demolition where a building is knocked down into rubble. It is the sudden, total disappearance of the idea of a building, where the bricks themselves stop being bricks and the mortar stops being sticky. The very language of construction is deleted from the universe. The energy involved in this transition is beyond comprehension, but it would not manifest as a blinding flash or a titanic shockwave in the way we picture explosions. The bubble wall is a front of pure potential energy being released as the Higgs field tumbles down its landscape. This energy reconfigures the vacuum itself, rewriting the operating system of spacetime in its wake. It is less like a wall of fire and more like a wall of absolute translation, converting the complex, structured code of our universe into a far simpler, likely barren program. Any information, any pattern, any memory encoded in the arrangement of matter, from the rings of a tree to the data on a hard drive to the neural connections in a brain, would be scrambled into nonsense by the new physics. There is no backup, no recovery. The past is not destroyed, it is rendered permanently unreadable. This forces us to confront a profoundly unsettling idea about cosmic endings. We naturally think of an end as a violent event, a collision, a collapse, a fiery consummation. But vacuum decay presents an end that is quiet, absolute, and intellectual. It is the end of meaning written into the laws of physics. The universe would not go out with a bang, but with a rewrite, a final edit that leaves the page blank in a way no force of nature ever could. This statistical reality paints a terrifying cosmic picture. If the universe is truly infinite, or even just unimaginably vast beyond our observable horizon, then every possible quantum event, no matter how improbable, is not just possible, it is inevitable. Somewhere out there, in the unfathomable expanse, the quantum dice have already rolled the wrong number. A single bubble of true vacuum has already nucleated. And from that point, the irreversible redefinition of reality began its march at the speed of light. We must then confront a haunting question. Could that wave of transformation already be on its way here? The mathematics of probability suggests that in an infinite cosmos, it is not just possible, it is almost a certainty. The universe may be a vast, quiet forest, and somewhere in its distant depths, a fire was lit an eternity ago. The flames are spreading tree by tree, and we have no way of knowing how close they are to our own little grove. The most unsettling part is the absolute silence of the approach. We rely on light to see the universe. We watch supernova explode and galaxies collide from billions of years in the past because their light has finally reached us. But this offers no protection from vacuum decay. The bubble wall moves at the ultimate speed limit, the speed of light itself. Any signal, any flash of radiation from the catastrophic rewriting of a star system at the bubble's leading edge would travel at exactly the same speed as the wall. The warning signal and the event are one and the same. There would be no advance notice, no distant flash on an astronomer's screen to study and dread. The first and only sign that our universe's stable era has ended would be the sudden, silent change in the rules of existence itself, arriving without a whisper from the dark. This logic forces us to view our entire observable cosmos, all 100 billion galaxies within our theoretical sight, in a terrifying new light. We may not be living in a stable, eternal universe. We may be living inside a temporary oasis, a vast but finite region of false vacuum that has, by sheer luck, remained undisturbed for nearly 14 billion years. Beyond the cosmic horizon, beyond the farthest light we can ever hope to see, the true vacuum may already reign supreme, its frontier creeping steadily closer on a timescale of eons. Our entire history, from the first stars to the rise of civilizations, could be unfolding in a bubble of borrowed time, a calm eye in a storm of cosmic transformation we cannot yet perceive. It is a humbling reminder that our perception of reality is limited not just by our instruments, but by the very laws of physics that dictate what information can reach us and when. Our safety may be an illusion crafted by the finite speed of light, a cosmic delay between a sentence being passed and its execution arriving at our door. The mathematics of this cosmic lottery are written in the particles we have already found. To understand whether our universe is perched on a cliff, physicists turn to the data, specifically to two of the most massive fundamental particles we know, the Higgs boson and the top quark. Their precise masses are not just random numbers, they are the dials that set the shape of the Higgs field's energy landscape, determining whether our valley has a secure floor or a hidden trapdoor. When researchers plug our best measurements into the equations, a sobering possibility emerges. The numbers suggest our vacuum might indeed be metastable. That deep, true valley likely exists, and we are not in it. Our universe appears to be resting in that shallow dip on the mountainside, stable for now, but not for eternity. This conclusion, however, comes with a universe-sized asterisk. The calculation requires extrapolating our known laws of physics across staggering energy scales, from the gentle world of particle colliders to the searing energies that existed a fraction of a second after the Big Bang. It is like using the physics of a flowing stream to predict the exact behavior of a tsunami. We are missing pieces of the puzzle, the presence of entirely new particles or forces predicted by theories like supersymmetry. could dramatically reshape the landscape, potentially building a wall around our valley and restoring perfect, eternal stability. The truth is, we are conducting the ultimate long-term experiment. Our continued existence, the fact that the stars still shine and atoms still hold together, is data. Every second that passes without the universe unmaking itself is a tiny piece of evidence that our vacuum is at least stable enough for now. This profound uncertainty is not a failure of science. It is a beacon illuminating the very frontier of our understanding. It shows us that the most fundamental questions about reality's permanence are still open, waiting for the next discovery, the next deeper look into the quantum code. We are living inside the test chamber, and the experiment is still running. Our continued existence is the first clue, but scientists are not content to wait and see. They have become cosmic archaeologists, sifting through the oldest light in the universe for scars of past catastrophes. The tool for this search is the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills every direction of space. This ancient light is a snapshot of the universe when it was only 380,000 years old, and etched into its subtle temperature variations could be the bruises of a violent past. If our cosmos is part of a vast multiverse where vacuum decay events happen in other realms, their aftermath might crash into our own. Picture two soap bubbles expanding in a sink. When they meet, they merge along a circular boundary. In the multiverse scenario, if a bubble of true vacuum from another universe collided with our expanding bubble of false vacuum during the universe's fiery infancy, that collision would have sent shockwaves rippling through the primordial plasma. Those ripples would leave a distinct circular imprint on the cosmic microwave background, a kind of cosmic birthmark. Astronomers have meticulously scanned the most precise maps of this afterglow, searching for these telltale circles, regions with unusual temperature patterns or specific gravitational wave signatures. They are looking for the ghostly echoes of a reality that once bumped into another. So far, no conclusive evidence has been found. The sky, at least within the limits of our observations, shows no obvious scars from such a monumental encounter. But the search itself transforms how we see the universe. It means that our most fundamental questions about stability and existence are not purely theoretical. They are empirical. We can literally look at a map of the infant cosmos and ask, are there cracks in the foundation? The absence of evidence is not the end of the story. It simply means that if our universe was born from such an event, it happened far beyond our observable horizon, or that the signatures are too subtle for our current instruments to detect. Each new, more sensitive telescope that peers into this ancient light is not just studying the beginning of everything. It is conducting a forensic examination, checking the cosmic crime scene for signs of a previous, unthinkable collapse. This turns cosmology into the ultimate detective story, where the clues are written in the cold whisper of radiation that has traveled for over 13 billion years, carrying secrets about whether our reality is alone or just one fragile island in a sea of constant, silent transformation. Our own presence in the cosmos may be the most compelling clue we have. This line of reasoning is known as the Anthropic principle, a philosophical lens that turns the observer into a piece of evidence. In its simplest form, it states that the universe we are capable of observing must be compatible with our existence as observers. Apply this to the specter of vacuum decay. If the quantum dice were heavily weighted, if the spontaneous nucleation of a true vacuum bubble were a common event on timescales of millions or even billions of years, the cosmic landscape would be littered with sterile, rewritten regions. The chain of events needed to produce a planet like Earth, life, and conscious beings contemplating the stars requires an unbroken stretch of stable physics for over 13 billion years. If the universe were routinely reset, that chain would have been snapped long before we ever arrived. The mere fact that we are here, asking this question, suggests something profound about our cosmic environment. It tells us we do not live in a universe where vacuum decay is a frequent, short-term hazard. Our existence is indirect, statistical evidence that our region of space, at the very least, has enjoyed an extraordinarily long run of stability. This offers a strange but powerful form of comfort. It means we are not living on the razor's edge of probability, where a cosmic catastrophe could be triggered tomorrow. The universe has likely already passed the most dangerous probabilistic milestones simply by lasting long enough for us to arise within it. We are not the audience for the first act of a cosmic drama. We are latecomers to a show that has been running smoothly for eons. This perspective, however, does not grant absolute safety. The Anthropic principle does not prevent a decay event from happening in the future. It simply suggests that such an event is improbable on human timescales. We might be living in a vast, unusually long-lived bubble of false vacuum within a grander multiverse where decay is common. Our safe neighborhood could be a rare cosmic suburb, a fortunate accident in a landscape of constant transformation. This thought connects our personal fate directly to the deepest laws of physics. Our ability to wonder about the end of everything is, in itself, a powerful argument that the end is not imminent. It grounds a terrifying cosmic possibility in the quiet reality of our own consciousness, reminding us that we are not just passengers in the universe, but active witnesses whose very presence helps to define the kind of universe we must inhabit. The sheer span of cosmic time redefines our sense of danger. To truly grasp the risk of vacuum decay, we must step away from human calendars and think on a scale that feels almost meaningless. Even if our universe is perched in a false vacuum, its half-life, the time it takes for there to be a 50% chance of decay occurring somewhere, could be unimaginably vast. We are not talking about millions or billions of years. The mathematics suggest a timescale that could exceed the current age of the universe by a factor of 10 to the power of 100 or more. That number is so large it has no analogy in our physical world. It is more than the total number of atoms in the observable universe multiplied by itself over and over again. On that scale, the probability of a decay event happening in any given year becomes not just small, but functionally zero for every conceivable human purpose. It is less likely than a perfect diamond spontaneously disintegrating into a pile of graphite dust in the next second, an event permitted by quantum physics but so staggeringly improbable it has never been observed in the entire history of the material. This cosmic perspective is a powerful corrective to our instinctive alarm. The universe operates on timelines that utterly dwarf not just human history, but the entire lifespan of stars and galaxies. Our civilization, for all its achievements, occupies a sliver of time so infinitesimally thin on this cosmic clock that it barely registers. The profound theoretical threat of vacuum decay, while illuminating the deepest nature of reality, translates into a non-existent practical risk for us, our descendants, or even for the future evolution of life in our galaxy. The true lesson here is not about an impending end, but about the breathtaking stability required for anything to exist at all. Our reality may be metastable, but its temporary nature is measured in epochs so long they border on the eternal from our point of view. We are living in a moment of profound cosmic grace, a stability so enduring that it has allowed the universe to grow rich with complexity, and for us to emerge within it, able to ponder the very forces that could, in a time beyond all comprehension, bring that story to a close. The ultimate safety of our universe may rest on a single, invisible wall. This is the energy barrier, the quantum mountain that separates our familiar reality from that deeper, truer vacuum state. The probability of a catastrophic decay event hinges almost entirely on two features of this barrier, its height and its width. Think of it like trying to roll a ball out of a valley. A gentle, low hill is easy to roll over, but a sheer, towering cliff face is another matter entirely. In the quantum world, the higher and wider this energy mountain is, the less likely it becomes for a random fluctuation to tunnel through it. The odds drop off exponentially, becoming almost impossibly small with each incremental increase. This is our first and most powerful mitigating factor against a sudden cosmic rewrite. Our current understanding of particle physics allows us to estimate the dimensions of this barrier, but the answer lies in a zone of profound uncertainty. The data we have, primarily from the mass of the Higgs boson and the top quark, sketches a landscape that suggests a barrier exists, but its exact shape is fuzzy, lost in the extrapolation to energies we cannot yet probe. This uncertainty is not a dead end, it is a frontier. It means the long-term fate of reality could be reshaped by a single new discovery. Imagine future particle colliders, machines of even greater power than the Large Hadron Collider, smashing particles together at energies that recreate conditions a fraction of a second after the Big Bang. In those collisions, we might find evidence of new particles or forces, entities predicted by theories like supersymmetry. The existence of such particles would not just be another entry in a physics catalog. They would act like architectural supports, buttressing the walls of our cosmic valley, making the energy barrier taller and wider than our current models predict. They could transform the universe from a precarious perch into a fortress of near-permanent stability. This connects humanity's most abstract scientific pursuits directly to the cosmos's ultimate destiny. Every experiment, every new datum from the frontier of particle physics, is quietly conducting a diagnostic on the universe itself. We are not just learning about the building blocks of matter, we are taking the temperature of reality, checking its vital signs for long-term health. The search for a deeper theory is unknowingly a search for cosmic reassurance, a way to measure the strength of the foundation upon which all of existence is built. The early universe holds another secret that could be our greatest shield. In its first fleeting moments, a process called cosmic inflation stretched the fabric of space itself at an exponential rate, far faster than the speed of light. This wasn't an expansion of matter into a void, but a rapid swelling of spacetime from a subatomic speck to a volume far larger than our entire observable cosmos. This primordial frenzy may have performed a crucial act of cosmic hygiene. If any true vacuum bubbles managed to form in that initial chaotic froth, the incredible stretching of inflation would have diluted them to near nothingness, pushing them effectively beyond the edge of our visible universe. It would have smoothed the quantum wrinkles, ironing the vacuum into a uniform, metastable state across the entire region we can now see. Think of it like blowing up a balloon with a tiny smudge of ink on its surface. As the balloon inflates to an enormous size, that smudge becomes a faint, almost invisible speck, lost against the vast new area. Inflation may have done precisely that to any early threats, giving our pocket of reality a clean, stable slate to begin its 13.8 billion-year story. This suggests our local cosmic neighborhood might be uniquely calm, a legacy of that ancient growth spurt. But the story of cosmic dynamics doesn't end there. The universe's current accelerated expansion, driven by the mysterious force we call dark energy, adds a new and ongoing variable to the equation. Dark energy behaves like a constant energy density inherent to empty space itself, and it contributes a term to the vacuum's total energy budget. This subtle, pervasive pressure could be acting as a stabilizer, gently tilting the energy landscape of the Higgs field in a way that reinforces our false vacuum, making that treacherous mountain a little wider or a little taller. The universe, it seems, is not a passive stage upon which this quantum drama plays out. Its own history and its present-day behavior are active, dynamic forces in this grand balancing act. The violent stretching of our infancy and the gentle push of dark energy today might be the unseen architects of our prolonged stability, quietly adjusting the parameters of reality to favor persistence over peril. The true power of an idea is revealed when it escapes the lab and enters our collective imagination. Vacuum decay has done exactly that, becoming a haunting presence in science fiction, where it serves as the ultimate antagonist, a force of nature rewritten. In the long-running series Doctor Who, a story titled The Satan Pit features an entity imprisoned at the edge of the universe, whose mere existence threatens to unravel the laws of physics, a clear echo of a vacuum metastability event. It is a villain that cannot be reasoned with or fought conventionally, representing a threat to reality itself. Similarly, Cixin Liu's renowned novel The Three-Body Problem introduces the concept of a dimensional strike, a weapon that lowers the dimensional structure of space, rendering civilizations helpless. While not identical to vacuum decay, it taps into the same profound fear, the idea that the universe's fundamental operating system can be hacked, leading to silent, inescapable erasure. These narratives are more than just thrilling catastrophe scenarios. They are cultural reflections, translating abstract equations into stories that probe our deepest anxieties. In a world filled with visible threats, vacuum decay represents the pinnacle of invisible peril, a catastrophe with no warning and no possible defense. It externalizes our subconscious understanding of reality's fragility, the nagging thought that everything we know rests on a foundation we did not build and cannot fully see. By personifying this threat or by setting stories in its shadow, science fiction allows us to confront the unthinkable from a safe distance, to ask what meaning and resilience look like when faced with absolute oblivion. These stories often shift the conflict away from defeating the force itself, which is impossible, and toward the human response in the final moments. They explore questions of legacy, connection, and what we choose to hold onto when the laws of physics themselves are being revoked. This transformation of a theoretical footnote into a narrative engine shows how science and storytelling intertwine. Physics provides the terrifying premise, a universe that might contain its own delete key. Fiction provides the framework to explore the emotional and philosophical consequences of that premise. It lets us rehearse in our minds the ultimate test of our values, not in the face of an enemy, but in the face of a silent, indifferent rewrite of the cosmos. Through these tales, the chilling equations of quantum field theory become a mirror, reflecting our own wonder, dread, and relentless search for meaning against the vast, impersonal backdrop of spacetime. This pursuit of knowledge carries a weight far beyond the laboratory. It forces us to confront a startling ethical question, one that sounds like science fiction but is grounded in real physics. Could our own experiments, our attempts to probe the universe's deepest secrets, inadvertently trigger the very catastrophe we fear? The scenario is both dramatic and deeply unsettling. Imagine a future particle collider, a machine of unimaginable power, concentrating energy into a volume trillions of times smaller than an atom, briefly recreating conditions not seen since the universe's first instance. In that fleeting, microscopic fireball, could we nudge the Higgs field just enough to tip it over the edge, creating the seed of a true vacuum bubble? For most physicists, the answer is a resounding and confident no. The energy scales required to meaningfully perturb the vacuum's stability are believed to be near the Planck scale, a realm of energy so far beyond our current or even conceivable future technology that it is like comparing a campfire to the core of a supernova. The safety margin, according to our best models, is astronomically vast, yet the mere possibility, however remote, opens a profound philosophical chasm. It asks us to consider a new form of responsibility, one that stretches from the control room of a collider to the fate of the cosmos itself. Do we, as a curious species, have a duty to weigh cosmic-scale risks in our quest for understanding? This transforms the scientist's work from a purely intellectual endeavor into an act of planetary, even universal, stewardship. every decision about pushing the energy frontier becomes a quiet referendum on how much we value the stability of reality itself against the hunger to know its origins. It is a burden no other generation has had to consciously bear, a direct link between human ambition and the fundamental parameters of existence. The consensus of safety is strong, but the ethical imperative to ask the question remains, reminding us that our greatest power is not just in discovery, but in the wisdom with which we choose to explore. Cosmic endings come in many forms, but none are quite like this. We often picture the universe concluding with a slow fade or a dramatic collapse. The Big Freeze or heat death is a quiet, drawn-out finale where the cosmos expands forever, stars burn out, and all energy gradients smooth into a uniform, lukewarm sea. It is a story of exhaustion, of the universe running down like a forgotten clock. The Big Crunch is its dramatic opposite, a reversal where gravity finally wins, pulling all matter and space back into a singular point, a mirror of the Big Bang. Then there is the more speculative Big Rip, where dark energy grows so strong it shreds galaxies, planets, and even atoms in a final, violent crescendo. These are all endings driven by gravity and entropy, playing out over timescales of trillions upon trillions of years. They are processes, however grand, that operate within the established laws of physics. Vacuum decay is something else entirely. It is not a consequence of the universe's expansion or its eventual contraction. It is a change to the operating system itself. Imagine watching a chess game where the pieces slowly wear down over eons until they can no longer move. That is heat death. Now imagine that halfway through the game, someone suddenly declares that knights now move in straight lines and pawns can fly. The game you were watching isn't just ending, it is being replaced by a different game with entirely new rules. Vacuum decay would not be the end of the universe in the sense of emptiness or collapse. It would be the end of our universe's specific set of physical laws. The space would still be there, but everything that gave it meaning, structure, and history would be translated into an alien and likely lifeless code. This distinction is what makes it so uniquely unsettling. Our greatest cosmic threats are about the loss of energy, light, and structure. Vacuum decay is about the loss of the very language in which those things are written. It asks us to fear not the darkness but the erasure of the page. The universe's silent hum is a ticking clock. Within the seeming emptiness of space, a fundamental rule of quantum mechanics is constantly at work, Heisenberg's uncertainty principle. This principle states, in essence, that on the smallest scales, nothing is ever perfectly still or perfectly defined. For a fleeting instant, a tiny region of space can borrow energy from nowhere, as long as it pays it back almost immediately. This lone shark of the quantum world operates on timescales so short they are meaningless to us, but its effects are everywhere. These momentary energy loans manifest as virtual particles, pairs of matter and antimatter that flicker into existence and then annihilate each other before any instrument can directly catch them. This ceaseless, bubbling activity is what physicists call the quantum foam, the fundamental texture of reality itself. It is not a metaphor. It is the engine of all potential change in the quantum realm, the source of Hawking radiation from black holes, and the subtle force that makes empty space not so empty after all. And it is from this frothy, energetic substrate that the unthinkable seed could sprout. Among the countless trillions of these random fluctuations happening every second in every cubic centimeter of space, one, by sheer statistical fluke, might borrow just enough energy in just the right configuration to do something catastrophic. Instead of creating a simple particle pair, it could nudge the Higgs field itself, not just a little, but enough to push it over the energy barrier and into that deeper, truer state. In that one, in a Googleplex event, a microscopic bubble of new reality is born. This is the stunning, almost poetic linkage at the heart of the vacuum decay hypothesis. The same quantum randomness that allows for the spark of creation for particles to appear from nothing also contains the blueprint for ultimate erasure. It ties the fate of galaxies, stars, and civilizations directly to a dice game played in the utter darkness between atoms. The probability for any specific fluctuation to achieve this is so low it defies human comprehension. You are more likely to shuffle a deck of cards into perfect order every second for the age of the universe and still not come close. Yet, because the universe is so vast and time so long, that non-zero chance translates into a perpetual background hum of existential risk woven into the fabric of everything. It means the stability of the cosmos is not guaranteed by immutable law, but is a dynamic statistical phenomenon, a fragile peace maintained by unimaginably favorable odds, moment by quantum moment. The equations that predict this cosmic fragility describe a landscape, not one of rock and soil, but a mathematical terrain of energy and possibility, a shape known as the Higgs potential. It is a multi-dimensional map where every point represents a possible value for the Higgs field, and the height of the terrain at that point represents its energy. Our entire universe corresponds to a single location on this map, a valley where the ball representing the Higgs field currently rests. This valley feels stable and permanent to us, but the full map reveals a startling truth. Somewhere else on this cosmic cartography lies a deeper valley, a basin of energy so low it makes our home look like a plateau. That is the true vacuum. The mountain ridge separating our valley from that deeper one is the energy barrier, the quantum cliff face that prevents an immediate and catastrophic slide. The ball in our valley does not have the energy to simply roll up and over that mountain, but through quantum tunneling, it has a vanishingly small chance to simply appear on the other side, as if a tiny doorway opened through the rock. The precise shape of this entire landscape, the steepness of our valley walls, the height and thickness of the mountain, and the depth of the lower valley are not arbitrary. They are calculated from the fundamental numbers of our reality, primarily the masses of the Higgs boson and the top quark. These are the dials that sculpt the terrain. A slightly different mass for either particle would warp the hills and valleys, potentially making our valley the deepest one, or erasing the mountain barrier entirely, leaving us on an unstable slope. This is why particle physicists are not just cataloging particles, they are acting as cosmic surveyors. Every collision in a giant accelerator like the Large Hadron Collider is an attempt to take a more precise measurement of these dials, to refine our map of this invisible, all-important landscape. Their work is a high-stakes cartography mission because the contours they are trying to trace dictate far more than what happens inside a detector. They sketch the boundaries of cosmic destiny itself, determining whether our universe is built on bedrock or perched above an abyss, waiting for a quantum tremor to finally find its true and final resting place. The thought of a universe rewritten is so final, it seems to leave no room for hope. But what if the story does not end with a blank page? Let us venture into the most speculative territory of all, a thought experiment about what might exist on the other side of that silent wall. If a bubble of true vacuum did not simply erase all information, but instead established a new, stable set of physical laws, could anything emerge within it? Our form of life is a delicate dance of carbon chemistry, reliant on the specific strengths of electromagnetism and the nuclear forces. In a new vacuum, those forces would be reconfigured, likely making atoms as we know them impossible. The periodic table would be meaningless, yet it is conceivable that different fundamental constants could permit other architectures of complexity. Perhaps structures could form from the interactions of entirely new particles, bound by forces we cannot name, following a logic alien to our own. It is a staggering concept that what we perceive as the necessary conditions for existence might only be a local set of rules, a single chapter in a much longer book. This pushes the idea of cosmic evolution to its absolute limit. Our universe, with its stars and galaxies, might not be the universe. It could be just one phase in a grand metastable sequence. A bubble of new vacuum would not be an end but a transition, a resetting of the cosmic stage where a different play with a different script could one day begin. The actors would not be made of atoms, the sets not built from molecules, but something would take the stage. This speculation transforms vacuum decay from a simple catastrophe into a possible mechanism of cosmic renewal. It suggests that reality itself might have a form of evolution, where less stable phases give way to more stable ones, and within those new phases, the potential for structure and perhaps even awareness emerges under laws we cannot fathom. Our existence, then, becomes a testament to one particular set of winning numbers in a perpetual cosmic lottery, a temporary configuration that allowed our specific story to be told before the wheel spins again. It is a humbling and strangely beautiful perspective that even the most absolute ending we can conceive might simply be a doorway to a different kind of beginning. Our maps of reality have edges, and we are staring right at them. Every confident statement about vacuum decay, every calculation of that staggering half-life, depends on a critical assumption that the laws of physics we have discovered here at low energies remain unchanged all the way up to the universe's most extreme scales. This is a breathtaking leap of faith. We are using the standard model of particle physics, a theory brilliantly successful in our labs and colliders, to predict behavior at energies trillions upon trillions of times more powerful. It is the scientific equivalent of studying a single snowflake under a microscope and then trying to forecast the climate of an entire planet for the next billion years. The equations might be elegant, but the territory they claim to describe is utterly alien and untested. This is the fundamental wall our understanding hits. The standard model is not the final word. It is a magnificent chapter, but we know the book is longer. Glaring mysteries like dark matter, dark energy, and the force of gravity itself, which refuses to be neatly woven into the quantum tapestry, are proof that our map is incomplete. These unknowns are not just gaps, they are potential continents that could reshape the entire landscape. The inclusion of new particles or forces, as predicted by theories aiming to solve these puzzles, could dramatically alter the shape of the Higgs potential. That precarious mountain barrier we worry about might not be a cliff at all, but the side of an impassable, fortified canyon wall, making our vacuum eternally secure. Or, in a more unsettling turn, new physics could reveal hidden pathways, making a transition easier than we ever suspected. The haunting possibility of vacuum decay, therefore, exists in a strange limbo. It is a specter conjured by our current best equations, a logical ghost in the machine, but whether that ghost is real or merely an artifact of our limited perspective is a question we cannot yet answer. It serves as a profound reminder of humility. Our science has revealed a cosmos of breathtaking grandeur and intricate order, but it has also illuminated the vast, dark ocean of what we do not know. The uncertainty is not a failure, it is the compass pointing toward the next great voyage of discovery. Every unanswered question about quantum gravity or dark matter is not just a puzzle, it is a variable in the ultimate equation of cosmic stability. We are left with a powerful duality, a theory that warns of an ultimate fragility, and the sobering awareness that the theory itself is a work in progress, a flickering lantern held up against the infinite dark. This cosmic fragility is not merely a threat, it is a clue. The possibility of vacuum decay forces physics to confront its most profound questions, moving us far beyond simple doomsday scenarios. At its heart, this is a story about measurement and meaning, the intense study of vacuum stability, of whether our universe sits in a true or false valley, is one of the most powerful tools we have for probing realms of energy we can never hope to recreate in a laboratory. By carefully measuring the mass of the Higgs boson and the top quark, and then extrapolating those numbers to the universe's first moments, we are conducting a forensic investigation into the birth of reality itself. Each decimal place of precision is like turning the focus knob on a cosmic microscope, giving us a sharper image of the primordial landscape. This work pushes our theories to their absolute limits, exposing their weaknesses and guiding us toward the next great breakthrough. It asks why the fundamental constants of nature have the precise values they do, a puzzle known as the problem of naturalness. Why is gravity so weak compared to the other forces? Why do particles have the masses we measure? The unsettling answer suggested by vacuum decay is that these values might not be necessary or finely tuned for life. They might simply be local, contingent facts, the way the temperature and rainfall in a particular valley are local facts on Earth. They are the numbers our region of space ended up with when the cosmic dice were cast, not the only numbers possible. This is a revolutionary shift in perspective. For centuries, science sought the eternal, unchanging laws governing the cosmos. Now, we must entertain the idea that those laws might be more like local bylaws, specific to our cosmic neighborhood and our epoch in time. This opens the door to breathtaking possibilities like the multiverse, where an endless froth of universes bubble into existence, each with its own random set of physical constants. In most of those universes, the numbers do not allow for atoms or stars or life. We quite naturally find ourselves in one of the rare outliers where they do. This transforms physics from a purely descriptive science into a historical one. We are no longer just cataloging how the universe behaves. We are piecing together the story of how this particular universe with these specific rules came to be. We are cosmic archaeologists sifting through the subatomic debris of particle colliders and the ancient light of the Big Bang to reconstruct a biography of reality. The haunting whisper of vacuum decay, therefore, is not a signal of impending doom, but an invitation to a deeper understanding. It asks us to consider that our home is not the entire mansion of existence, but a single, beautifully appointed room within an infinite, dark, and mostly empty estate. And in that realization lies not fear, but a profound sense of wonder at the sheer improbability of our being here at all, able to listen to the universe's quietest and most revealing secrets. This revelation strikes at the very core of our understanding. For centuries, science has operated on a fundamental assumption that the laws of physics are universal and eternal, the unchanging rules of a cosmic game. The speed of light, the gravitational constant, the charge of an electron, these were not just numbers we measured. They were the bedrock of reality itself, the absolute truths upon which everything else was built. But the possibility of vacuum decay shatters that assumption. It tells us these constants are not written in stone. They are written in the state of a quantum field. They are the local weather conditions in our particular valley of reality, not the climate of the entire cosmos. If the Higgs field can fall into a different state, then every single one of these fundamental numbers can be rewritten in an instant. The speed of light could become a different number, the force that holds atoms together could vanish, the very concept of mass could be redefined. This is a philosophical earthquake. It means our universe is not the only possible universe. It is simply one possible arrangement, one specific solution to equations that may have countless other solutions. The fact that our constants allow for stars, planets, and life is not a necessary truth, but a contingent, almost accidental fact. We are not living in a universe designed with us in mind. We are living in a universe that, by a particular roll of the quantum dice, happened to produce conditions where beings like us could arise to notice it. This idea, known as the Anthropic principle, moves from a curious footnote to a central character in the story. Our existence becomes the evidence that we live in a rare kind of cosmic neighborhood, one stable and structured enough for the long, slow story of evolution to unfold. But it also means that beyond our horizon, the rules could be profoundly different. This introduces a radical kind of fragility to everything we know. The permanence we sense in the rising sun and the fixed stars is an illusion of timescale. We are not witnessing eternal laws, but extremely long-lived local customs. This aligns with some of the most profound questions in philosophy about the nature of being and necessity. Philosophers have long debated whether the world as we find it is the only way it could be, or merely one way it happens to be. Physics is now providing a startling answer. It suggests our reality is soaked through with contingency. The fact that we are here to ask these questions does not prove the universe is necessary. It simply proves that we are the products of one particular fortunate set of circumstances in a much vaster and more varied landscape of possibility. This transforms our place in the cosmos from central actors in a singular drama to temporary residents in one room of an infinite mansion, most of whose rooms are dark, silent, and governed by rules we could never comprehend. It is a humbling perspective, but also one filled with a strange and majestic wonder, for it means the universe is far richer, far more mysterious, and far less predictable than we ever dared to dream. Our reality may be a temporary arrangement, a cosmic interlude in a much longer, stranger story. This knowledge carries a humbling power, one that redefines our place in the grand scheme. For all our technological triumphs and cultural monuments, we are residents of a universe whose deepest laws might be provisional, a set of rules that could, in a time beyond all comprehension, be rewritten. This isn't a call to despair or nihilism. It is an invitation to a profound shift in perspective, a cosmic humility. It reminds us that we are not the center of the story, but participants in a dynamic, evolving cosmos filled with processes that operate on scales and timelines we can barely fathom. These processes, from the quantum froth of empty space to the silent potential for its transformation, unfold with an indifference to human hopes and fears. We did not build this stage, and we do not control the script, yet here we are, conscious witnesses to its majesty. This humility can be strangely liberating. It shrinks our petty concerns to their proper scale against the backdrop of galactic superclusters and eons of cosmic time. More importantly, it sharpens our appreciation for the rare and beautiful anomaly we inhabit. This stable pocket of reality, with its just right constants and forces that allow for complexity, is not a given. It is a gift of staggering improbability, a temporary island of order in a sea of potential chaos. Every sunrise, every breath, every connection we make is happening within a fleeting window of cosmic grace. Recognizing its fragility does not diminish its value, it magnifies it. This perspective can fuel a renewed sense of wonder and a deeper commitment to understanding the grand tapestry of which we are a small but curious part. Our drive to map the Higgs potential, to probe the early universe, to seek a theory of everything, becomes more than just an academic pursuit. It is how a transient species on a tiny rock in a temporary universe reaches out to touch the edges of eternity, trying to read the signature of the cosmos before the page perhaps turns. The quest to know our cosmic fate is already underway, with experiments designed to probe the very foundations of reality. Our next generation of tools will act as cosmic surveyors, mapping the energy landscape of the Higgs field with unprecedented precision. Future particle colliders, machines far more powerful than today's, will smash particles together at energies that brush against the universe's first moments. In those microscopic fireballs, we will not just find new particles, we will measure the behavior of the Higgs boson and the top quark with a fineness that current technology can only dream of. Each decimal place of accuracy in these masses is like adding a new contour line to our map of the Higgs potential, revealing whether the valley we inhabit has steep, secure walls or a hidden, treacherous slope. This is not abstract science. It is a direct investigation into the architectural integrity of spacetime itself, conducted one collision at a time. Beyond our accelerators, our telescopes are also on the case. The James Webb Space Telescope and its successors will peer deeper into the cosmic microwave background, that ancient afterglow, searching for the faintest imprints of primordial violence. They will look for the subtle, circular patterns that could be the scars of a long-ago collision with another bubble of reality, or for anomalies that suggest our vacuum's properties were different in the distant past. Even the study of ghostly neutrinos or the ripples in spacetime from colliding black holes detected by gravitational wave observatories can offer indirect clues. These phenomena test our physical models under extreme conditions, revealing whether our equations hold firm or hint at new physics that could reshape the entire stability calculation. This multi-front effort transforms a haunting theoretical question into a concrete experimental program. We are not just waiting to see what happens. We are actively building the instruments to diagnose the universe's long-term health. The path forward is clear, a coordinated campaign across particle physics, astronomy, and cosmology. Each new datum, whether from a tunnel deep underground or a telescope orbiting 1,000,000 miles from Earth, is a piece of the puzzle. The goal is to turn the specter of vacuum decay from a chilling possibility into a resolved chapter in our understanding, either confirming a strange fragility or finally granting us the reassurance of a truly stable cosmos. The answer is out there, written in the particles and the ancient light, waiting for our next generation of explorers to read it. The cosmos may be far more prolific than we ever imagined. This is where the haunting possibility of vacuum decay collides with one of the most expansive ideas in modern cosmology, the multiverse. Picture not a single universe, but a vast, eternally inflating foam of realities. A cosmic sea where new universes constantly bubble into existence, each with its own random set of physical laws. In this breathtaking picture, vacuum decay is not merely a silent end. It could be the very engine of creation, the mechanism that spawns new pocket universes from the fabric of old ones. Our own stable region of spacetime, with its specific Higgs field value and familiar constants, might not be the original. It could be the offspring, the result of a decay event that occurred in a parent universe with entirely different rules. In that parent cosmos, a random quantum fluctuation tunneled through an energy barrier, birthing a bubble of what we now call reality. That bubble inflated violently, becoming the vast expanse we call home, while the parent universe, with its alien physics, continued on its own path, perhaps completely unaware of the new realm it had spawned. This reframes everything. The erasure of one set of laws becomes the genesis of another. A catastrophic transition in one region of the multiverse becomes a Big Bang event in another. It integrates vacuum decay into a grander, cyclical narrative of eternal change, where realities are not permanent but proliferating, each one a temporary configuration in an infinite tapestry of possibilities. This perspective offers a strange kind of solace. It suggests that even if our local vacuum is metastable, its potential transformation is not a meaningless extinction. It could be a link in an endless chain, a way for the cosmos to explore every possible combination of physical laws, giving rise to islands of structure and perhaps life in a boundless ocean of silent, empty space. We are no longer contemplating an absolute end, but a possible rebirth under a different sky, governed by different stars. Our journey ends not with a definitive answer, but with a transformed perspective. We have peered into the quantum heart of nothingness and found it humming with potential, a reminder that the cosmos is built on foundations far stranger than simple emptiness. The idea of vacuum decay, a silent bubble rewriting the laws of physics, stands as one of the most profound thought experiments science has ever produced. It stretches our understanding of reality to its absolute limits, forcing us to question the permanence of everything from the atoms in our hands to the distant light of ancient galaxies. This is not a prediction of doom, but a testament to the power of human curiosity to explore even the most unsettling possibilities. The mathematics suggests our universe is likely stable for timescales so vast they border on the eternal from our vantage point, a cosmic safety margin of almost unimaginable depth. Yet the mere existence of this hypothesis changes how we see our home. It reveals a universe that is dynamic, contingent, and possibly just one arrangement in a much grander tapestry of existence. The constants we rely on may not be eternal truths, but local conditions, a fortunate and temporary alignment that allowed our story to be told. This realization carries a quiet power. It invites a deep and humbling wonder, a recognition that our ability to ponder these vast ideas is itself a miraculous product of cosmic stability. It encourages us to look at the night sky not just as a static picture, but as a temporary and breathtaking chapter in an ongoing saga of transformation. If you found this exploration of cosmic fragility as fascinating as we did, consider subscribing for more journeys to the edge of understanding. We would love to hear your thoughts on this ultimate what-if scenario in the comments below. What does it mean to you to live in a universe that might contain its own quiet final edit? Thank you for exploring this profound mystery with us.